Welcome to the lesson on laws of electricity, Ohm's law and Watt's law. Let us take a look at the learning objectives. By the end of this lesson, you will be able to describe Ohm's law and Watt's law, which are the fundamental principles in electrical engineering. Understanding the interrelation between these two laws is critical as they govern the behavior of electrical circuits. You will be able to perform calculations using Ohm's law and Watt's law to determine unknown values in circuits, enabling them to analyze and design electrical systems effectively. You will also grasp the significance of these laws in electric vehicles, where efficient energy management is essential for performance and sustainability. Ohm's law is considered one of the fundamental principles in electrical engineering. It establishes a relationship between voltage, current, and resistance in an electrical circuit. Understanding Ohm's law is important for analyzing and designing electrical circuits of all kinds, from simple circuits to complex systems. The law is named after the German physicist Georg Simon Ohm, who formulated this principle in the early 19th century. Ohm's groundbreaking work laid the foundation for understanding electrical circuits and paved the way for modern electrical engineering. The law states that the current flowing through a conductor, such as a wire, between 2 points is directly proportional to the voltage applied across those points. In simpler terms, if the voltage increases, the current flowing through the conductor will also increase, and vice versa. Understanding the dynamics of electricity involves grasping the essential concepts of voltage, resistance, and current. Voltage, sometimes referred to as electromotive force, can be pictured as the pressure that drives current through a conductor as depicted in the image. It represents the potential energy difference between 2 points in a circuit. Resistance, on the other hand, signifies the difficulty that voltage encounters as it travels through a conductor. Think of it as the barrier that opposes the flow of electrical current. Current denotes the rate at which electric charge flows through a conductor. It represents the movement of electrons along a path, driven by the voltage and regulated by the resistance. The Ohm's law triangle is a visual representation of the mathematical relationship as shown in the image. Putting these into words, Ohm's law states that voltage equals resistance multiplied by current. Resistance equals voltage divided by current, and current equals voltage divided by resistance. Voltage is measured in volts, current is measured in amperes, and resistance is measured in ohms. Imagine we have an electrical circuit with a current flowing through it of 2 amperes, and it includes a resistor with a resistance of 1 ohm. To find out the voltage across this circuit, you simply multiply the current by the resistance. So it is 2 amperes multiplied by 1 ohm, which equals 2 volts. Therefore, in this scenario, the voltage across the circuit would be 2 volts. Let us take a detailed look at the relationship between voltage, current, and resistance. According to Ohm's law, 1 volt of pressure is needed to drive 1 ampere of current through 1 ohm of resistance. Ohm's law provides a versatile tool for calculating one value of an electrical circuit if the other two are known. For instance, if we know the voltage V and resistance R in a circuit, we can easily calculate the current I using the formula I equals V divided by R. Moreover, Ohm's law clarifies how changes in voltage or resistance affect current flow. If resistance remains constant, increasing the voltage will boost the current. Conversely, if voltage remains constant, increasing the resistance will diminish the current. This interactive relationship illustrated in the table is important for understanding and manipulating electrical circuits, allowing engineers to design and optimize systems for various applications. Now, let us take a look at Watt's law, another fundamental principle in electrical engineering. Named after the Scottish engineer James Watt, this law defines the amount of electrical power in a circuit as the product of voltage and current. It establishes a direct relationship between power, voltage, and current. Watt's law serves as an important tool for engineers and technicians in designing, analyzing, and optimizing electrical circuits for various applications, ensuring efficient energy utilization and system performance. Watt's law states that the power in watts in an electrical circuit is determined by multiplying the voltage in volts by the current in amperes. The Watt's law triangle is a handy tool used to understand the relationship between power, voltage, and current in an electrical circuit. It consists of 3 sides representing P, V, and I. To use the triangle, you cover up the quantity you want to find. For instance, to find power, you multiply voltage by current, so P equals V times I. Similarly, to find voltage, you divide power by current, so V equals P divided by I. And to find current, you divide power by voltage, so I equals P divided by V. The Watt's law triangle simplifies calculations and helps solve for unknown quantities in electrical circuits. Imagine that we have an electrical circuit that has a voltage of 12 volts and a current of 2 amperes. Using Watt's law, we can calculate the power consumed by the circuit by multiplying the voltage and current, resulting in a power consumption of 24 watts. Watt's law is essentially an extension of Ohm's law, which connects voltage V, current I, and resistance R in an electrical circuit. The formulas for calculating any combination of electrical units, including voltage, current, resistance, and power, are conveniently displayed in what's known as the magic circle, as showcased in the image. This circle serves as a reference tool for electrical calculations, making it easier to determine unknown quantities in circuits based on the given information. Some of these practical applications will help you understand how to calculate values in electrical circuits. For instance, if we have a light bulb with a voltage of 110 volts and a power consumption of 60 watts, we can determine the current using the formula P equals V to Messier. By rearranging the formula to solve for current, we find that the current is 0.54 amperes. Similarly, consider a toaster oven plugged into an outlet with a voltage difference of 120 volts and a current of 10 amperes. Using the same formula, we find that the oven consumes approximately 1,200 watts of power. Let us consider another common household appliance, such as a steam iron, and use Watt's law and the magic circle to calculate unknown values. The appliance is rated at 1,000 watt and is plugged into a 120 volt outlet. The question is to calculate the current drawn by the steam iron and its resistance. To calculate the current drawn by a 1,000 watt steam iron plugged into a 120 volt outlet, we can use Watt's law, which states that power equals voltage times current. By rearranging the formula to solve for current, we get current equals power divided by voltage. Plugging in the given values, we find that the iron draws a current of approximately 8.33 amperes. Next, to determine the iron's resistance, we can use the magic circle, which relates voltage, current, and resistance. Since we know the voltage and current, we can calculate the resistance using the formula resistance equals voltage divided by current. Substituting the values, we find that the appliance has a resistance of about 14.4 ohm when plugged into a 120 volt outlet. This example demonstrates how Watt's law and the magic circle can be applied to everyday appliances to determine their electrical characteristics, such as current draw and resistance. By understanding these concepts, we can better comprehend the power consumption and safety aspects of the devices we use in our homes. Let us now explore how Ohm's law and Watt's law influence the design and operation of electric vehicles, shaping their functionality and sustainability. These principles are applicable to various systems within a BEV, including motors, batteries, and charging systems. They provide essential guidelines for engineers to understand and optimize the performance of these components. Ohm's law and Watt's law aid in the development of sustainable features in BEVs. For example, they enable the implementation of regenerative braking systems, which convert kinetic energy into electrical energy during braking to recharge the battery. Moreover, these principles assist in managing energy efficiently within the vehicle, optimizing battery usage and extending driving range. They also contribute to thermal management systems, ensuring that components operate within safe temperature ranges, enhancing the overall reliability and longevity of the vehicle. Furthermore, the application of Ohm's law and Watt's law in electric vehicles is critical for effective current and voltage management. These principles enable engineers to set voltage and current within safe limits, preventing electrical overloads or short circuits that could jeopardize vehicle safety. Ohm's law and Watt's law inform the proper design of circuit protection mechanisms such as fuses, circuit breakers, and other protective devices, ensuring the reliability of BEV electrical systems. Beyond safety considerations, these laws play a crucial role in enhancing battery efficiency and management, optimizing the performance and lifespan of BEV batteries. Additionally, they contribute to maximizing electric motor efficiency, promoting overall system efficiency and sustainability in electric vehicles. In conclusion, mastering Ohm's law and Watt's law is essential for engineers and technicians in various aspects of electrical engineering, particularly in battery electric vehicle design and analysis. These fundamental principles are critical for managing electrical systems safely and efficiently, ensuring optimal performance and energy usage in BEVs. Ohm's law and Watt's law shape every aspect of BEV design, from motors and batteries to charging systems and energy management features. By understanding and applying these laws effectively, engineers and technicians can enhance BEV capabilities and implement sustainability features, ultimately contributing to the advancement of electric vehicle technology and the transition towards more sustainable transportation solutions. Thank you.